Hello and welcome to our second lesson on polynomials. And what we've learned so far is how to work with complex and radical numbers. It's a review from earlier. Today we're going to, and actually the rest of the chapter, learn about a family of functions called polynomials. You've seen them as linear, quadratic, maybe even cubic. And then later in the chapter we'll do something with rationals, which means similar functions but negative exponents. So, to get going here, today what we want to learn is how to identify the degree and leading coefficient of a polynomial, how the degree and leading coefficient will affect the graph, and how to describe some key features of a polynomial. Finding zeros and factoring. Where does the function equal 0? What we want to do here is focus on what makes the function equal 0, and if the function is factored, we can see values for x that will make the whole function equal 0 because we can get one of the factors to equal 0. So a rather simple quadratic here, we would see that x squared minus x minus 2 factors into x plus 1 times x minus 2. Knowing that you have two values that are multiplied that make it equal 0, at least one of them must be 0. That means x plus 1 or x minus 2. So we just choose the opposite value. Negative 1 plus 1 is 0, or 2 minus 2 is 0. And those are both zeros of the original function, where the original function, it may not be as obvious. Some basic polynomial examples. Quadratic, you've seen, has a degree 2. Cubic, a degree 3. Quartic and quintic, not used a lot in this class, but 4 and 5 is the highest degree for those polynomials. But we could keep going. And some basic definitions. The degree of a polynomial is the same as the greatest exponent of the variable. And we typically use x for this. The leading coefficient is the coefficient of the highest degree polynomial. And the zero of a function f is an x value. We use the letter c where f of c equals 0. So the value we would call a 0 is the x value that when plugged into the function makes the whole thing equal 0. And essentially that's an x-intercept. What degree is the function? And what is the leading coefficient of the function? So if we look at f of x, we look for the biggest exponent, in this case 6. We would say the degree for f of x equals 6. And then the number in front of that term will be what's called the leading coefficient. And I will often just use LC. All right. Look at g of x. It's a little bit deceptive. You need to look for a polynomial in standard form, and in this case we'd have to rewrite it, or since the question is simply to find out some values, we could just look at it, but I'll write it in standard form, helping us see that 7 is the degree, and then the leading coefficient is negative 4. Okay, and those two things are what really affect the shape of the graph, so we'll want to be very clear on where we find those values. We get to something called the fundamental theorem of algebra. What it states is that an nth degree polynomial function has exactly n zeros, and this means there are n zeros, n values of x you can plug into the function that make the graph cross the x-axis, or the whole function equals 0. So if you have a linear equation at degree 1, you would see that the line crosses the x-axis in exactly one place, and actually that would be a real 0. If you have a parabola, you'll have exactly 2 zeros. We talk about real and complex. A while back you were taught that there are the quadratic formula, and we always made sure the radical term, the discriminant it's called, was a positive value. But if you had a parabola that opens up and is above the x-axis, you're still going to have two zeros. They're just going to have i's in their solution, imaginary solutions or complex. So let's take a quick look at the graphs of quadratic functions. There's a few features we want to point out. The y-intercept is an obvious one, so we look at that, but it's not the most important necessarily. We obviously care about the vertex, something we'll call a turning point, and as well what the zeros are from the fundamental theorem of algebra. So if we look at some of these examples, you'll understand how they compare in relation to their zeros and vertex and how they open up or down. And we want to get familiar with those things and how that's indicated by certain values, specifically the leading coefficient and the degree. You'll notice a negative 1x squared opens down, a positive 1x squared opens up. Same thing down here. The negative 1x squared opens down, positive 1x squared opens up. In addition, the y-intercept is obvious when we have a graph in standard form. We just plug in 0 for x and the variable terms go away, so we're just left with y-intercept that I've written in blue here. There's also always two zeros, but in this case on the top we're going to have two real. This one we're going to have one real, something we're going to call a double zero. And then these are both going to have complex zeros because it doesn't cross the x-axis. And so we got some stuff to get into here. Consider the zeros for the following quadratics. In this example, we're going to have two zeros that are real on the left. We could say x equals negative 2 and 3 are zeros. For the second example, the zeros, and this, we're going to call it zeros, but it's x equals 1, 2, 3, 4, but it's a double zero. So we would say 0 of multiplicity 2. It's a multiple zero. And then the last one, they're going to be complex zeros. We can't tell what they are from the graph. Takes a little more algebra work, but those will be complex zeros. So get familiar with the amount as well as the type of, whether it's a multiple zero or a complex zero. Back to the point about the vertex, as a graph turns and goes from increasing to decreasing or the other way around, decreasing to increasing, in red here we point to all the actual turning points, places where things go significantly different in the graph. And then there's something called an inflection point, a little tougher to see or notice, but it's where the concavity changes. And what you want to notice there is if you are increasing but increasing at a different rate and then changing to still increasing but at a different rate, there's a place, it's not always obvious, that the graph has gone from increasing, in this case, at a faster rate to then increasing at a slower rate. And that's, you typically look at something like this and call it like an exponential kind of a thing where it's increasing faster and faster, but when it gets to the inflection point, that's when it changes to increasing at a slower rate. So there's something to pay attention to, and it's rather subtle. I think you'll notice though. And now we want to ask some questions. These are going to be fundamental questions we get into for all polynomials. So as they look easy for quadratics, be thinking how you would generalize or expand your understanding to higher degree polynomials other than the ones you've seen for years now in Algebra 1 and Algebra 2. What's the number of zeros for a quadratic? Well, a quadratic is a degree 2, and by the fundamental theorem of algebra, the number of zeros equals the degree of the polynomial. In the case of a quadratic, that's 2. So remember, that will include the complex zeros as well, whether it crosses the x-axis or not. There's a way to make it 0. What's the maximum number of critical points, or changes in concavity, for a quadratic? And remember, that's where the graph may turn completely from increasing to decreasing, or even how it changes from faster to a slower rate. Those are inflection points. There will always be one for a quadratic, and generally there are a maximum of n minus 1, n being the degree, turning points for a polynomial. And last, how many zeros are possible for a quadratic? Well, there are 0 if the quadratic does not cross the x-axis, but there's still zeros. There's just no real numbers. They're going to both be complex. 1 if it just touches. That would be a 0 of multiplicity 2, or we could call it a double 0. And then last, if the quadratic crosses the x-axis twice, there are 2 real zeros. That was basically what you dealt with mostly in Algebra 1. Didn't have to deal with complex numbers. Okay, this is the graph of y equals x minus 4 squared. So it's just translated to the right 4. And what I want to ask is, what's unique about this 0? We've talked about it. It's not just a 0, it's a 0 of multiplicity 2, or something we could call a double 0. Now you'd be thinking, if this polynomial had a higher degree, we obviously could have higher degree zeros as well. And now we look at graphs of cubic functions. Similar view we want to take. What are the critical features happening here? The y-intercept's easy to find, so I pointed those out. It's not a really critical thing. It's just useful for sketching the graph with limited information. But the zeros we definitely care about, as from the fundamental theorem of algebra. So if you look at this top left one, we've got zeros of multiplicity 1 all the way across the board. They're all real zeros. On the right, we see there is a 0, but there's only 1, and it's a degree 3 polynomial. It stretches. You might remember this from a direct inverse, y equals x cubed. So what we'd call this one is a degree with a 0, with a multiplicity of 3. And now we look at the equation in the bottom left, and what you notice here is there's a few negatives, so it's a little deceptive, that negative, and of course that minus 2. The graph will look as shown here. And now we look at this graph in the bottom left, and there's a few negatives in here. It can be a little bit deceptive. You might think this thing would translate to the right, but because of the negative out in front, the graph is shown above here. There's a 0. It's a real 0, but it's a 0 of multiplicity 3 in this case, just like the previous problem. And now we look at this last example, and we notice that it has 3 zeros that are real, just like the first example, and they each have a multiplicity of 1. You may have noticed also that the leading coefficient has an effect. If the leading coefficient here is negative, it really ends up looking kind of like a negative slope. And if the leading coefficient is positive, it has a positive slope with some squiggles.